Okay, so let's go through some of the inferential statistics, some of the key formulas here, and just point out a few things. Standard error of the mean, so this is the standard error. Notice you're going to have a standard error for any statistic you look at, anything you're going to try to estimate in the population, which a lot of the times in basic statistics is just the average. You just want to estimate the average of the population. And so you create a sampling distribution of that average of the mean, and then you get the standard deviation of that sampling distribution. And that's what this is right here. That's called the standard error. In other words, if you would take a sample and get a mean, about how far are you going to be off of the population mean? That's the standard error. And it's very closely related to the population standard deviation. Notice that it's going to be quite a bit smaller because it's going to get divided by square root of sample size. So this is precisely why when we increase the sample size, we're making this number down here bigger. And when you divide by a bigger number, you end up making the thing on the left here smaller. In other words, when we increase the sample size, we decrease the standard error, which is a good thing. We want low error because it allows us to make a more precise estimate. Now, because we don't actually know the population standard deviation most of the time, what we do is we just use the sample standard deviation instead. And just a little bit of an adjustment here, but that will give us an estimated standard error. Okay, now when we're trying to figure out this population mean, so we have a sample, but what we really want to know is the average of the population mean. So our best guess is our sample mean. Doesn't matter how big our sample is, how big the population is, the best guess that we have to go on from a single sample is going to be the mean of our sample. But we know that that's probably not exactly right, and so we create what's called a confidence interval. Now what the confidence interval is, it starts with the mean and then it goes a little bit in both directions. In this case, we go t-crit standard errors to the left and t-crit standard errors to the right. So standard error of the mean, that's what we just looked at, the formula. That was this S of m right there. What's this t-crit? Well, the t-crit is going to depend on what we choose for our confidence interval. So if we choose a 90% confidence interval, the t-crit's going to be different. A 99% is going to be different. It's based on the t distribution, the probability that we have the population mean somewhere out here, basically. So 95% chance that the population mean is going to be somewhere in this confidence interval, somewhere t-crit standard errors to the left to t-crit standard errors to the right from our best guess, from our sample mean. This is going to create kind of a low-end guess and a high-end guess, and somewhere in between the low-end and high-end, we're going to catch the population mean most of the time. 95% on average of the time we'll catch it. Sometimes it'll be way out here. So that's where that formula comes from, though, that minus and plus. It's just we're measuring the distance away from the mean in terms of standard errors. Now, what we can also do is start with the null hypothesis. So notice here, we're starting with the sample mean and then kind of building an interval around it. We're actually doing the same type of thing here, but in a different way. Here we're seeing how far away are we. So this is our sample mean right here. This is our population mean. How far away are we from the population mean in terms of standard errors? How many standard errors are we away? That's why we divide by standard error of the mean on the bottom. And that gives us our t-stat. The t-statistic is just saying how far away from the population mean was our sample in terms of standard errors. And then we can compare this to a critical region that's built around the null hypothesis to see whether we're inside or outside of that critical region. So really we're doing the same thing except backwards. Here we're starting with the sample mean and creating an interval around it. And then what we could do actually, the confidence interval, if we look at where the null hypothesis is, the null hypothesis of the population mean, if it's outside here somewhere, outside of our confidence interval, that would be the same as rejecting the null. If it's somewhere inside here, we would fail to reject the null. Here, on the other hand, we're seeing how far away we are from the null hypothesis, how far our standard, how far our sample mean is away from the null hypothesis in terms of standard errors. And then we compare that to the t-distribution. And if we're outside, if this t-stat is too far away, if we're just too many standard errors away from the hypothesized null hypothesis mean, population mean, then we just reject the null. So both of those two are showing the statistical significance. Now, the confidence interval does give a sense of effect size, but when we're talking effect size, we really want to know how far apart the populations are. So this, it's labeled a little bit differently, but let's just assume that this is the null hypothesis mean, and this is the sample mean that we have, and we've determined that they're two separate distributions. So this was far enough away that we decided this sample mean is coming from a different population than this null hypothesis population mean. So in a sense, there's two different distributions, and we want to know how far apart they are. Well, the null hypothesis mean we'll already have set up. The other distributions mean, of course, we don't know, but remember what our best guess was. Our best guess was the sample mean here, right? And so we would take the sample mean and the null hypothesis mean. Again, it's not quite labeled the same here, but the point is we would take the difference between those two means and then convert it to number of standard deviations. So sample mean minus population mean, null hypothesis population mean, and then convert that to standard deviations by dividing by standard deviation. Notice this is not standard error. This is simply our sample standard deviation, which is our best guess. Ideally, we'd like to know the effect size in terms of population standard deviations, but we usually don't have that information, so we just divide by the sample standard deviation and use that as our unit. Okay, standard error of the difference between the means. So in the first few slides, we were looking at a population mean, a single population mean. This is different now. Now we have two different populations. Maybe it's females and males. Maybe it's people who are taking the drug and people who are not taking the drug. Maybe it's two different races. Whatever it is, we have two different populations, and we get an average for both of those. So we're taking a sample from each of those populations. Let's just say males and females. And we have a sample of males, a sample of females. Each one of those samples will have an average. What we really want to know is we really want to know the difference between the male population average and the female population average. You know, is there any difference, or are they pretty much the same? But since we don't know that, we take a sample from each of them, get the sample means, and again, that's our best estimate. So let me just go to this slide real quick. So when we subtract the two sample means, that's going to be our best guess at how far apart the actual population averages are. Now, when we're dealing with the difference between means, we have a different standard error. So whatever we're trying to find out in the population is going to have its own standard error. It's going to have a slightly different distribution of the standard error, and this is specifically the standard error for the difference between means, the difference between the two groups that we're looking at. So it's similar. You'll remember the standard error was just the standard deviation divided by n, And since we have this square root and a square inside, you can see similarities there. But because we have two different groups that could have two different sample sizes, we're talking about an independent t-test here, so we certainly could have different sample sizes, could have different variances here. So this is going to give us the standard error of the difference between the means. And since we can't get these two things up here, now we can get the sample sizes, we can't get these two variances, we estimate them each with the sample variance. So this gives us our standard error. Then when we go to build the confidence interval, it's the same exact process. So we get our best guess based on the sample. That's going to be as close as we can with the data we have. And then we're going to subtract a little and add a little to create this confidence interval for where the actual population could be. Our best guess is hopefully close, but likely not exactly right. So we create this confidence interval. Notice that we do exactly the same thing that we did before. We take our best guess and minus t-crit standard errors, and then we take our best guess and add t-crit standard errors. So we go t-crit standard errors in both directions. Again, what's the t-crit? It's in that t-distribution based on whatever we choose, 95%, 90%, 99%. That's something that we can look up then to find what that what that confidence level will associate with in terms of the t-distribution. And then when we go to the actual t-test, so we wouldn't have to. We could do a null hypothesis with the confidence interval. All we'd need to look for is the null hypothesis inside our interval or outside of our interval? And almost always, when you're comparing two groups, what's your null hypothesis? The null hypothesis is there isn't a difference. In other words, that mu1 minus mu2 equals 0. So our null hypothesis would be 0. If 0 is outside of this 95% confidence interval, we would reject the null hypothesis. If 0 is somewhere inside this, for example, if we had -3 to 5, then 0 would be somewhere inside of there, then we would fail to reject. So we're using the confidence interval to do a null hypothesis test. Or we could do it directly, calculate the t-statistic, difference between the sample means. This we've already talked about. Our hypothesized difference between the population means, our null hypothesis, not the alternative hypothesis. The null hypothesis is these two things are the same thing. So if you subtract two things that are the same thing, this will just end up being 0. So this entire part of the equation would cancel out in most cases if your null hypothesis is the population means are the same. And then you would divide by the standard error. So again, we're taking our best guess, seeing how far apart the two are in the samples, and then we're just putting it in terms of standard errors. And then finally we get effect size. Remember that the effect size for a single mean, we would have the sample mean minus the null hypothesis mean over the standard deviation, sample standard deviation. So that's not our standard error. We're just seeing how far off were we in terms of standard deviations. And we typically want this to be high because we want to show a pretty strong effect here. Same thing. The difference in our sample means minus the difference in the population null hypothesis means, this will typically be 0. So this will typically be 0. And standard deviation, but we have an issue here because we have two different populations. So we divide it by a pooled standard deviation. If we can reasonably assume that that the variances are the same in the two populations, then we can just combine it into this pooled standard deviation and get the difference between the two sample means there in terms of that. So if these sample means are very far apart, that's going to create a higher D, right? A higher effect size. If the sample for the females and the sample for the males are quite far apart, we're going to have a higher effect size. Or if we have a low standard deviation, that's also going to create a higher effect size because it means whatever effect we saw was worth